topic that we have in this section is surface area for a parametrized surface. Penelope the mouse heard that we were doing surface area again, and she wanted to make sure that she came and waved her ears at you to say hello and to wish you luck with this new topic. Okay, thank you, Penelope. Good job. Okay, so what we're going to do is actually very similar to what we did when we had surface area for the graph of a function, where z was a function of x and y. We're basically going to be calculating small sections of the tangent plane. But our formula for calculating that is going to be a little bit different because, of course, we're describing our surface differently. So it should come as no shock to you that we are going to do a 4-step process, and that step 1 is to chop. Okay. So what I've drawn up here is essentially we've got a parametrization of a surface where u and v are my parameters, and we're mapping some region D in the UV plane to some surface that I'm calling S in the XYZ coordinate system. Okay. So this is a potentially curved surface that I have over here in 3 space. Okay. Now when we chop, we generally chop up the domain. So I'm going to chop D, the region in the UV plane, into nice little rectangles. And of course that's going to involve just making a bunch of vertical slices and a bunch of horizontal slices. And although I don't have to, I'm going to use a regular partition so that all of these little subrectangles are going to have the same width, which we'll call delta U, and the same height, which we'll call delta V. That just gives us less to keep track of. All of those rectangles are the same size. And of course, chopping D into little pieces induces a chopping of S into little pieces. So all of those vertical lines are going to become these. These would basically be what we call constant U curves, because notice a vertical line is what I get when I'm holding U constant. And all of those horizontal lines would become constant V curves, because a horizontal line is what I get when I hold V constant. So chopping D into little rectangles induces a chopping of S into little patches of surface. Okay. Now, it's not always going to be the case that you can see things so clearly. My region D has 4 corners and my region S has 4 corners. That's not always the case, because we've seen that we can map a rectangle to a sphere. And while technically that's not smooth because we have an issue at the very top and the very bottom point of that sphere, that's close enough to smooth that we can basically work with it. Okay? So I've drawn this so that it's easy to see the connection between the parts of D and the parts of S. It's not always going to be quite that clear, and that's totally fine. Okay. All right, step 2, we're going to try to approximate. So I want to try to approximate the surface area of one of these little patches that I have right here, okay, whose boundaries would be 2 constant U curves and 2 constant V curves. Okay. So what I'm going to do in order to do that is I'm going to approximate this with a parallelogram that's determined by the tangent vectors. So I'm going to choose, just because it's convenient, the lower left-hand corner as my representative point. So I'm going to just call that P star. Okay. Now, if this was the ijth rectangle, I'd probably call that Pij star. Since I'm just illustrating this with one rectangle, I'm going to omit the subscripts and just say that's my point for this rectangle and this patch of area. Okay. So this right here then would just be the point R of P star. Okay. And I can take a look and I can say if I want to approximate this curve right here, which actually let's draw this in purple as well. Okay. This curve would be the constant v curve that we have right here along the bottom. I can approximate that by taking a vector, whoops, let's actually make it tangent to the curve, by taking a vector that's tangent to the curve at that particular point to give me the right direction, and then I'll scale that vector so that it has approximately the right length. So finding this vector is going to be a two-step process. I need to figure out what vector points in the right direction, and then what do I scale it by to make sure that it has the right length. Okay. Well, if this curve right here was what I get by holding v constant, then along here, u is the only variable that's changing. So a vector that points in that direction would be the partial of r with respect to u, evaluated at this representative point, p star. Okay. That's what would be tangent to this curve. So that gives me the correct direction at this point. Now, if I just have that, its length might be way too long or way too short. Probably way too long, because we're chopping this, remember, up into very, very small pieces. Now, what each of those things is, this would be the partial of x with respect to u at p star, comma partial of y with respect to u at p star, comma partial of z with respect to u at p star. Okay, those are the components. There we go. Those are the components of this. So each of these components is a rate of change. But we've seen before that rates of change are actually the amount that the output variable would change if we change the input variable by an amount of 1. Okay. For example, 60 miles per hour is a rate of change. If I travel at 60 miles per hour for 1 hour, my position will change by 60 miles. So the rate of change corresponds to the amount that things would change over a change in the input of just 1. But if I take a look, I'm not changing u by 1, I'm changing u by the amount delta u. Okay. So what I'm going to do is I'm going to take this vector and I'm going to scale it by a factor of delta u. Okay. So the derivative gives me the correct direction. Scaling it by delta u makes it so that I'm scaling each of these by a delta u. So instead of getting the approximate amount that x changes over a change of 1 in u, I'm getting the approximate amount that x changes for a change of delta u in u. Okay, so then I'm going to do exactly the same thing here. Now, these vertical-ish sides are basically the image of these vertical sides here, where I was holding u constant. So if I'm holding u constant, v is the only thing that's changing. So the vector that points in the right direction here would be the partial of r with respect to v, and to get it to be approximately the right length, I'm going to scale that by the amount that v actually changes. So if I do that, I've approximated those two sides with vectors. I can then create this lovely parallelogram, and I can say that I'm going to approximate the area of this little patch of the surface S with the area of this parallelogram. Okay. All right. So these vectors, notice, are vectors in 3 space. The partial derivative of r with respect to u and v is going to have 3 components, because I'm going to have the partials of x, of y, and of z. So since these are vectors in 3 space, I will get the area of this parallelogram by simply taking the cross product. So I can say not just the cross product, the magnitude of the cross product. So I'm going to want the magnitude of del r del u at p star scaled by delta u, crossed with delta v times del r del v. at P star. Okay. That's going to be the exact area of this parallelogram, which will be the approximate area of this little patch, because that parallelogram would be a portion of the tangent plane that's tangent to the surface at this particular point. Okay, so this video's been going for a while, so I'm going to pause this video here. I'm going to stop this video here and come back with a second video in a moment. What we'll do is talk a little bit about how to simplify this and then work through the rest of our 4 steps, so adding and taking a limit.